introducción. Buenas tardes y bienvenidos a esta edición de las Jornadas Astronómicas de Almería. Todos los años amenazamos con volver y cumplimos, como veis, volvemos. Voy a ser breve, no brevísimo, porque tengo ya al invitado de hoy, que es a quien habéis venido a ver, para la primera conferencia, que por cierto, alguno no sabe de qué va a ir la conferencia, pero la mayoría supongo que sí, va de agujeros negros. Pasa que como la ha titulado Un viaje de 40 años, me han preguntado, oye, ¿de ese viaje de qué va? Pues va a ir de agujeros negros. Muchas gracias a las instituciones que hacen posible que se celebren y que estén consolidadas ya las Jornadas Astronómicas de Almería, que son fundamentalmente el Ayuntamiento, el área de Cultura y la Diputación, y también la Universidad de Almería. Y como estos días la mayoría sé que repetís, pues todos los días hablo un poquito al principio, os iré contando más cosas de momento. Vamos a recibir al invitado de hoy, le va a presentar el vicerrector de investigación de la universidad, y después nuestro amigo John Beckman, al que casi todos conocéis, hará ese tipo de traducciones que él hace habitualmente, que son muy buenas, pero a veces pone cosas de su cosecha también, como sabéis. Vale, pues nada, bienvenidos y muchas gracias por venir, por llenar el Teatro Apolo, que es lo que nos estimula para seguir haciendo más jornadas. Gracias.
Bien, buenas tardes a todos. Bienvenidos al Teatro Apolo, a esta inauguración de la 11ª Jornada de Astronomía. Hoy tengo el privilegio, el honor, la suerte de presentar a Reinhard Genzel, aquí a mi izquierda, Premio Nobel de Física en el año 2020. Reinhard es alemán, es decir, de aquí al lado, muy cerquita de nosotros, en Europa. Nació en 1952 y fue galardonado, como he comentado, en Premio Física del 2020, junto al británico Roger Penrose y la estadounidense Andrea Ghez, por su hallazgo sobre agujeros negros, especialmente por el descubrimiento de un objeto compacto supermasivo en el centro de nuestra galaxia. El doctor Genzel estudió física en la Universidad de Friburgo y en la Universidad de Bonn, donde realizó su doctorado, además también en el Instituto Max Planck, sobre radioastronomía, en 1978. Entre 1978 y 1980, pues, se marchó a Estados Unidos a seguir investigando, donde fue becario postdoctoral en el Centro Harvard-Smithsonian de Astrofísica en Cambridge. Y de 1980 a 1982 pues fue becario Miller de la Universidad de California en Berkeley, trabajando en espectroscopía de infrarrojo lejano. Posteriormente fue nombrado profesor en la Universidad de Múnich, en Baviera, donde sigue siendo actualmente profesor honorario desde 1988. En 1999 fue nombrado profesor titular de la Universidad de California, Berkeley, donde estuvo anteriormente becado. Es miembro científico de la Sociedad Max Planck desde 1986 y director del Instituto Max Planck de Física Extraterrestre en Garching, en Baviera. Es miembro de la Academia Europea de la Ciencia y de la Academia Alemana de las Ciencias Naturales, entre otras instituciones. Sus investigaciones se han centrado en los agujeros negros masivos y en la formación de estrellas dentro de la galaxia, así como la formación y evolución de la galaxia, que estudia con espectroscopía de infrarrojos, submilimétrica y milimétrica, y con imagen de alta resolución, así como aplicando interferometría espacial. Ha sido el primer astrofísico que centró sus esfuerzos en seguir el movimiento de la estrella en el centro de la Vía Láctea, y consiguió demostrar que estas orbitan alrededor de un objeto muy masivo. Finalmente, este objeto se descubrió que era un agujero negro de unos 4 millones de masas solares y actualmente ha sido bautizado como Sagitario A. Por sus investigaciones, el profesor Genzel ha recibido muchos honores y premios, entre ellos la medalla Otto Hahn de la Sociedad Max Planck en 1980, la prestigiosa beca Miller, que he nombrado anteriormente, de la Universidad de California en Berkeley, el premio Tycho Brahe de la Sociedad Astronómica Europea en 1912 y la medalla Herschel de la Real Sociedad Astronómica Británica en 2014, así como diversos doctorados honoris causa en distintas universidades. Creo que el turno, y estoy todo esperando a que tome la palabra el profesor Genzel, con que, profesor Genzel, the floor is yours. Thank you very much. Como ha comentado Pedro San José, ocupará mi lugar ahora el profesor John Beckman, que hará de traducción simultánea, y veremos todo cómo lo va a hacer realmente bien.
Good that we can see you, because otherwise you might have disappeared in the black hole. Ladies and gentlemen, I'm very pleased to be here and talk to you about an important issue of modern astrophysics, but also astronomy, and that is black holes. And as you will see, this subject has, over the last 100 years, advanced from a theoretical speculation to something where we can work in detail on as experimental physicists.
El tema de los agujeros negros es un tema que durante un siglo se ha adelantado de algo totalmente teórico a algo que se puede trabajar en detalle y una parte real de la física. No sé si pueden bajar un poco las luces generales. Dale.
Okay, so the story I will tell you is how we've come to be here, in my case, after 40 years of working on this and other subjects as an experimentalist, and showing you that black holes are not anymore subject of science fiction. I'm sure you're all experts in black holes and science fiction, but this is real hardcore physics.
Sí, ahora va a hablar de los agujeros negros reales, no los de ciencia ficción. Estoy seguro que todo el mundo aquí sabe, experto de agujeros negros en ficción, pero eso no lo es, eso es real.
Okay, so I'll start by inviting you on a trip with a computer traveling at about 10 to the 12 times the speed of light, a little fast as you will see, from our Milky Way to our neighborhood where there are other galaxies.
Va a enseñar una película que un viaje a 10 a 12 veces la velocidad de la luz para ver temas de cómo se forman las galaxias.
galaxies are the largest world islands, you could say, for normal material, normal matter, like us. They typically consist of 500 billion to 1,000 billion stars. And then there's also a material we call dark matter in these galaxies, which actually dominates the total mass of these galaxies. And in our universe, there are billions and billions of galaxies. So they are the subjects of much study in modern astronomy. We now know that the first galaxies formed only a few 100 million years after the Big Bang, and have since evolved into these systems you've just seen.
Las galaxias son grandes unidades que forman el universo. Contienen entre 5.000 millones de estrellas y 5 millones de millones de estrellas. Hay millones y millones de galaxias y ahora sabemos por el James Webb que las primeras galaxias formaron solamente 200 millones de años después del Big Bang.
Now, galaxies are kept together by gravity. We human beings know about gravity. Every one of you knows gravity. Because if you jump up from your seat, you sure come down very quickly. And so it is. These galaxies are held together by gravity. And we humans, studying the stars and our solar system, know, of course, about the work of Galilei, Copernicus, Newton, and Kepler, who a few hundred years ago basically explained how the solar system, with the sun dominating at the center and then the planets orbiting around that sun on circular or elliptical orbital paths, were held together by gravity. So the solar system is held together by gravity. And let me just say, the sun, of course, to us here, especially in Almería, is because it is so clear because you see its radiation. But for the solar system, even if the sun wouldn't shine, the planets would still go around the sun because of the action of gravity.
Todos sabemos lo de gravedad, sabemos si saltamos en el aire vamos a caer inevitablemente. Las leyes básicas que controlan los movimientos de los planetas, todo el mundo sabe que son de Galileo, después Kepler, Copérnico, Kepler y Newton, que infirió que lo que mantiene como una unidad el sistema solar es la gravedad. Y es cierto que aunque en Almería nosotros recibimos la luz solar y mucha, no es la luz del sol que mantiene el sistema solar, es su gravedad.
Now, 107 years ago, Albert Einstein presented in Berlin his new theory of gravity, the general theory of general relativity, which was similar to that of Newton, but it has some very substantial changes, and let me try to explain those changes to you. So in the picture of Newton, gravity is a force from one mass on another, from the sun to the planets. And that force in the picture of Newton is basically propagating through space at infinite speed. You just put the mass there, and then the force of gravity is everywhere. That is not the case in Einstein's theory. Look at this picture here. Einstein proposed one should look at gravity as a dent in or a curvature change in the space-time surrounding a mass. That mass, which dominates in this case the yellow thing, would then change the space-time curvature around it such that another mass, here this little red thing, would not go in a straight line, but would go the smallest distance, which actually brings it close to the yellow mass. So that's the equivalent of what Newton had said, but the difference here is that these dents in space-time propagate at the speed of light. They are not there instantaneously.
Bueno, la diferencia principal entre la teoría de gravedad de Newton y de Einstein es que en el caso de Newton la fuerza de gravedad se propaga con velocidad infinita. Pones una masa en un sitio y la otra masa instantáneamente siente la atracción de la primera. Mientras que en Einstein, con la teoría de Einstein, una masa distorsiona el tiempo-espacio de tal forma que la segunda masa se mueve en una curva. Y esta distorsión se propaga no instantáneamente, sino a la velocidad de la luz. Esa es una diferencia importante entre las dos teorías.
Now, the second important difference in Einstein's prescription has to do with light. It was known through experiments by Michelson and Morley in the late 19th century that this fastest communication in nature is the speed of light. Nothing can go faster than the speed of light, independent of what you read in science fiction novels. That's just a fact established by scientific measurement. And speed of light is really the maximum, and comes the next thing, light also experiences gravity. That it did not in Newton's theory, although others during Newton's time discussed it, but it was really Einstein who said no, it is light which also experiences gravity.
Pues había dos otras cosas que en la teoría de Newton la luz no nota la gravedad y mientras que en la teoría de Einstein la gravedad afecta a la luz, y en la teoría de Einstein la velocidad de la luz es la máxima velocidad posible. Y eso se estableció por experimento también.
Okay, so now in this picture which you see here, we have the Earth on the left side, then we have the Sun on the right in the center, and behind that Sun is a star, a distant star. And so Newton's description of the motion of light towards the Earth across the limb of the Sun is a straight line, because photons, light, don't see gravity. But in Einstein's theory, that's not the case, because there, indeed, also the photons, also light, sees gravity and is bent, as you see in this little graph. Now, as we look back from the Earth to the star, of course, our eye extrapolates along a line, and that line leads us to a position up there, not where the star really is, but at a larger distance from the Sun. And that Einstein could calculate, a very small amount, but one which one could in principle measure.
Pues el diagrama muestra qué pasa cuando la luz de una estrella pasa al lado del Sol rumbo a la Tierra, donde se observa. Al sentir la gravedad, se mueve en una curva, y al ver el rayo que llega, el ojo ve la estrella a lo largo de la línea recta. Y es una diferencia en posición. Y esa diferencia calculó Einstein y predijo cuánto se podía medir.
So this was in 1915. 4 years later, there was a occultation of a star field in the southern Atlantic, and astronomers went there and in fact started measuring exactly these things, namely how the positions of stars changed as the Sun was occulting part of the field, and from that they could derive this angle, and they found exactly what Einstein had seen in his theory. So it became very clear that photons are affected by gravity. That really is a very important step, as you will see in the next slide.
En 1921 el famoso eclipse del Sol y la ocultación del Sol de un campo de estrellas permitió a observadores, Eddington siendo uno, que medir ese cambio de ángulo y resultó un valor, exactamente el valor predicho por la teoría de Einstein. Muy importante.
Because from this prediction by Einstein to the next big step is not very much, and that brings you to the issue of black holes. And three more of the people you see on these pictures, Carl Schwarzschild, Roy Kerr, and Roger Penrose, who all worked on this problem throughout the next 50 years. So let's see what they basically calculated. So here we have the sun, and suppose we have a rocket on the surface of the sun, and we would like to fly with that rocket into infinite space, so to speak. You can do that from Earth, in principle. You can do it from the sun, and you can calculate that the speed is 600 kilometers per second. But if we now imagine in our minds another sun, which has the same mass as the sun, but a smaller radius, then the gravity on the surface of the sun is larger because the radius is smaller. And you can calculate again what the escape speed of the rocket is. And in this case, if the sun, in this other sun, is only 3 kilometers in size, the speed is 300,000 kilometers per second. And that's the speed of light.
Entonces, para entender cómo funciona una masa del Sol, pero mucho más compacta, si un cohete necesita escaparse de la superficie del Sol, el Sol real tiene que salir a 615 kilómetros por segundo. Si ahora alguien, una mano de Dios muy potente, comprime el Sol a un radio de 3 kilómetros, entonces el mismo cohete tendría que llegar a 300.000 kilómetros por segundo, que es la velocidad de la luz, para escapar. Y no podía, claro.
Okay, so with that, we're almost there with the black hole, because we now have the sun to make only a millimeter smaller, because then the escape speed is greater than the speed of light, and that means that all what is behind the so-called event horizon, inside of this event horizon, which is 3 kilometers minus 1 millimeter, so to speak, cannot communicate with the outside, certainly not through particles, but also not through light. That's a black hole.
Y si a ese Sol lo comprimes 1 milímetro, entonces nada puede escapar de este límite, nada, ni partículas ni luz, y entonces ese objeto es un agujero negro y el límite se llama el horizonte de acontecimientos o de eventos.
Okay, so I don't want to get into more details now on black holes. It's a very interesting issue, of course, but the main thing we now need to learn is, okay, obviously black holes are black. That is, they don't emit light, not within the event horizon. So how can you see them? How can you test that there is a black hole, if there would be one? Well, the answer is, go back to our solar system, which we discussed, and put it around this black hole. Then, of course, the planets in that solar system also would move in orbits, circular or elliptical orbits, and the same Kepler's laws, which we know from our solar system, would be true here as well. And by measuring the speed of the planets in this system, you can measure the mass of the central object, even if you cannot see it.
Entonces la pregunta es, si nada puede escaparse del agujero negro, ¿cómo sabemos que está ahí? Paso 1. Usa ese nuevo Sol compacto, el agujero negro, lo pones en el centro del sistema solar y miras las órbitas de los planetas. Van a seguir girando, porque la masa es igual. Y entonces, aunque hay una masa ahí que no puedes ver, puedes detectarla por su gravedad. en un sistema solar hipotético.
Okay, so far we have talked about mathematics. Mathematics is what's leading to predictions which could be tested. Einstein became very famous, as we all know, and but it took until the mid-1950s or 60s before astronomers were, so to speak, ready to join the hunt. Namely, to ask the question, are these objects called black holes, which come out of the theory, really there? Are they realized in nature? And the first, and I would say at this point, let me just say the one I will discuss here, are the so-called quasars. Quasars are very bright radio sources which were discovered in the 1960s, highly variable. But if you look at them in the optical, as you see here, you see a faint little star. Very faint star, not very attractive, not very exciting at all. But if you look at the spectral properties of this quasar light in the optical, you see very sharp lines. And these sharp lines are due to things like hydrogen and helium and so forth, but all redshifted in this object here by 16%. And that redshift could be due to the expansion of the universe, such that as we go and look at a distant object that is moving away from us, in redshifting all the spectral lines.
Entonces, entre Einstein y la realidad de los agujeros negros pasaron casi 50 años. Y los primeros objetos que tenían que ver con agujeros negros realmente eran los cuásares. Los cuásares se descubrieron, parecían estrellas muy débiles, como puntuales como una estrella, pero al obtener sus espectros, su velocidad se medía a una fracción importante de la velocidad de la luz. Y eso es muy raro, implica que están en una parte del universo en expansión y muy distantes. Y eso salió como una rareza difícil de explicar.
So for this 16% in this quasar, if this is due to the expansion of the universe, the object really is 2.4 billion light years away from us. So light takes 2.4 billion years. So that's a significant fraction of the age of the universe. And of course, we know that as you move an object away from you, the light which emits arrives at our place much dimmer. So if you correct for this dimming due to the distance, the total energy production in this little quasar thing is 1,000 times as much radiation as the entire Milky Way. But all of this comes from a volume of less than a light year.
Pues el problema era que tú puedes usar la velocidad para calcular la distancia, y la distancia de este objeto era 2,4 billones de años luz. Si después calculas cuánta energía debe emitir para nosotros verla, es 1 millón de veces mayor que la de toda la Vía Láctea, en un volumen del tamaño de un año luz. Imposible.
So as in the 1960s, a number of theoretical astrophysicists thought about how you could produce this much radiation, paradoxically, the idea came up by black holes. Now you say, wait a second, black holes, you just told us light cannot escape from black holes. True, within the event horizon. But if you have material falling into a black hole, say in this case, in a spiralized fashion, then before the material disappears behind the event horizon, the gravitational energy can be freed. And that's very, very efficient in converting the rest mass energy of a particle into radiation.
Pues alguien dijo, eso debe ser porque hay un agujero negro en el centro. Pero la pregunta surge, pero si luz no se puede escapar de un agujero negro, ¿cómo puede emitir tanta energía de luz? Y la respuesta es que no viene dentro del agujero negro, sino de la materia que se atrae y cae hacia el agujero negro y se convierte en energía de forma muy eficiente. Y eso sí produce tanta luz.
Okay, so that's a nice story, but you don't have to believe me. That's the essence of hard sciences. I have to convince you through experiments that this is so. And what is the experiment you would like to make? Well, I told you already. To measure actually the motion of this gas as it falls into the center of this galaxy, and you want to see very high velocities and at small radii. So that's the experiment you'd like to do. But this object here is so far away that certainly in the 1960s and 70s that was not possible. Lyndon Bell and Rees, two very famous theoretical physicists in the United Kingdom, made a proposal. They said, well, these quasars are very rare. Maybe that's because very rarely do black holes accrete so much material to become so bright. But maybe black holes as such are common. Only they're not fed very well in most of the galaxies. Maybe all galaxies have black holes, including our own. Well, then you don't have to go all the way to quasars to try to see whether at the centers of galaxies are black holes. Maybe you go to nearby galaxies, including, in particular, our own.
Entonces, esta idea de que puede ser un agujero negro produciendo tanta energía está bien, pero hay que comprobarla. Para comprobarla hay que medir la velocidad de la materia que se cae y órbitas alrededor para definir su tamaño. Un quasar está tan lejos que no se puede hacer. Todos varios astrónomos decían, bueno, quizás hay agujeros negros grandes en los centros de más galaxias, incluso en nuestra propia galaxia. En este caso, a lo mejor está cerca para poder medir esas propiedades del gas o de las estrellas alrededor.
Okay, so let's take a look. Let's fly from our position in the Milky Way into the center. Now, there is a little bit of a problem. The galactic center is very close, only 27,000 light years away. But as you see here, in addition to the stars, there's also this dark stuff. That's dust. That dims the light, and in fact, it dims the optical light completely. So you cannot see the galactic center in the optical. You can see it in the radio and also in the infrared, which we are seeing now. And when you end up in the center of our Milky Way, there is an enormously dense star cluster. So that's the location you might suspect there to be a central black hole.
Pues observando el centro de nuestra galaxia, es muy denso, es un problema que hay muchísimas estrellas en medio, si quieres ver al centro, y luz visible, no solamente hay muchas estrellas, sino hay mucho polvo interestelar que bloquea la luz. Si observas en el infrarrojo, en radio, pero en infrarrojo sobre todo, puedes observar las estrellas muy cerca del centro. Eso es lo que hay que hacer, usar el infrarrojo.
So when that was done in the 1970s, for the first time in the radio band, one would discover a very compact radio source there, this source we call Sagittarius A star, at the core of a very dense star cluster, which is this blue collection of blue points. And then in addition there's gas, ionized gas in pink and neutral gas in green. And so the idea had been to measure the motions of these gas clouds through their Doppler motions along the line of sight and determine whether that might point towards a very large mass there.
En los años 70 del siglo pasado empezaron a usar ondas radio para medir las nubes de gas alrededor del centro de la galaxia y a ver si estas nubes se movían con velocidades muy altas, suficientemente altas como para indicar que se estaban cayendo a un agujero negro hasta la fuente central que se llama Sagitario A estrella, A asterisco, que se identificó como el punto central de la galaxia.
And indeed, the radio astronomers, when they used their ever better telescopes, found remarkably compact sizes for the radio source of only, say, 100 microarcseconds. That's on the moon about this much. So that's a very, very compact source. And Charles Townes in Berkeley, Nobel laureate for the invention of the maser and laser, later became interested in astronomy, and he knew how to build equipment to do infrared spectroscopy. I became one of his postdocs initially, and then a colleague on the faculty, and we together built equipment where we measured these motions of these gas clouds. And what we found was basically that, yes, in the center of this central region, there seems to be a compact and concentrated mass, a few million solar masses in mass. And that could be a black hole. But the question is, and we'll continue as we go through this talk, must it be a black hole? Are there alternatives? And the answer is yes, because for a few million solar mass black hole, the distances of these gas clouds are a few million times the event horizon, so much other things could happen and be in there, faint stars, neutron stars, and so forth. So the evidence were beginning to be there, but it was not clear yet.
Pues las medidas utilizando radio encontraron la masa de la fuente central como unos pocos millones de veces la masa del Sol. Que entonces podría ser un agujero negro. Pues la cuestión es que podría ser, pero no es seguro, porque las distancias eran tan grandes de esas nubes que dejaron lugar a otros tipos de fuentes muy compactos, muchas estrellas de neutrones. Podría ser otra causa. Y para realmente intentar determinar todo, Charlie Townes, que vino aquí en una de las primeras jornadas, desarrolló equipo de infrarrojo para afinar esta medida, y Genzel era uno de sus postdocs en este proceso.
Okay, so we started doing this work and had this evidence, but it was clear we needed better information and more convincing evidence. How can you do this? First off, you need higher spatial resolution. You have to be closer to the central source. That means you have to have bigger telescopes so that you have sharper images. The next is that you want to have traces of gravity, which are really truly the best you can find. And these are not these gas clouds which you can push around with forces also other than gravity. And so these other traces are stars. So the next years were filled with technology, building better equipment, building bigger telescopes, etc., which kept us busy for the next decades.
Entonces tenían que desarrollar la técnica, tenían que construir telescopios mayores para mejor resolución angular y tenían que usar trazadores diferentes, estrellas que son puntuales y que dan mucha más resolución más cerca del supuesto agujero negro.
Okay, let's do that. This plays a key role in the work. At the same time, our American colleagues started using the Keck telescopes on Mauna Kea, and so to speak, an international race started. The Europeans were in Chile and the Americans on Mauna Kea. And we started measuring these motions of stars. And in the left picture there, you see pictures of the star field around Sergei star, which is a cross, in 3 different years. Red is year 1, yellow-green year 2, and blue year 3. And you can clearly see that stars close to Sergei star move very, very rapidly, about 1,000 times as fast as the Earth around the Sun. So that was, by 95, the first very clear evidence. Both groups had it, and for a central mass.
Entonces, hemos visto los telescopios que forman el VLT, Very Large Telescope, en Paranal, Chile, de los europeos, y simultáneamente los norteamericanos empezaron a utilizar los telescopios Keck en Hawái y empezaron una carrera, se nota ahí Genzel y Andrea Guest, que estaban en los Kecks, y obtuvieron estos campos de estrellas cerca de Sagitarios a estrella, donde se notó movimientos muy rápidos, 1000 veces más rápidos que los planetas alrededor del Sol. Y eso fue ya en los años 90 una pista muy importante sobre si Sag a estrella es un agujero negro.
So by the end of the 1990s, we were very sure there is a central mass. It looked good. This could be a black hole, but again, must it be one? And the answer is no, because we are still about 100,000 times away from the event horizon. So we need help. Bigger telescopes were not an option at that time, but nature can help. And nature can give us stars which get very close. And we didn't expect that actually to happen, but nature helped us. So we got stars like this one here on a highly elliptical orbit. And the position of Sagittarius A star, the radio source, likely the source, the location of the black hole, is that circle and the dot in the lower left. And that's where the star moved by in the year 2002. Then only 15 light hours away. 15 light hours is about 3 times the orbital radius of the planet Neptune, and all of that with a velocity of about 2.7% the speed of light. And we knew, okay, well that is really convincing evidence, because that's the same mass I talked to you before on the gas and on the motions of the stars, but now clearly within about 1,000 times the event horizon size.
Entonces, la evidencia previa era muy sugerente, pero todavía no conclusiva, y después la naturaleza ayudó, porque se encontró una estrella, la estrella S2, que tiene una órbita, aquí se ve, cerca del agujero negro, que es el círculo con un punto en la parte debajo del diagrama, que pasó solamente 3 veces la distancia Neptuno-Sol desde el agujero negro, muy cerca, y eso ya era un punto clave para determinar que sí, que es un agujero negro.
Okay, must it be a black hole? The same question I asked already several times. Now I would say most of the astronomy community in 2002 would have said yes. But the physicists were not yet impressed. They said, you must measure better, plus all your conclusions here is sort of an exclusion of other things, and you have not tested general relativity. Is it really true, or so close to a black hole? So all of these comments were there. So what can we do? Well, we have an orbit now. We have an orbit, and we knew in 2002 that that star would be back in 2018. And that's the critical thing, because now we had preparation time, 16 years, to improve our apparatus by another, and you will see about a factor of 20 over what we could do back then, in order to see the effects of general relativity and really go very close to the central object. But in the meantime, both groups basically observed the wonderful world of the region around the black hole.
Bueno, en 2002 ya tenían esta casi prueba, pero los astrónomos muy contentos, pero los físicos escépticos, porque decían, bueno, necesitamos más seguridad, más precisión, pero S2 tenía toda su órbita, entonces tenían 16 años para prepararse, para mejorar el equipo, y mejoraron la precisión por un factor 20 para medir muy bien la órbita de esta estrella milagrosa.
So by the time the star came back in 2018, we didn't have only one star, but as you see, a whole bunch of them with beautiful orbits, each and every one being a precise instrument, so to speak, to measure gravity. And the new trick for us was to not just use one of the 8-meter telescopes, but to combine the 4 8-meter telescopes on Parnell Mountain to a telescope of 200 meters in diameter. And then you can, within a given year, see the motions of the stars as they parry around the black hole on solar system scales in exquisite precision.
Entonces, no solamente mejoraron su técnica, pero podían utilizar todos los telescopios del VLT para obtener un telescopio de diámetro efectivo de 200 metros. Entonces, como se ve en este diagrama, podían determinar las órbitas de varias estrellas con precisión exquisita.
So with this data we then now have in hand since about 5 years or so, we can really test general relativity around this black hole candidate, and also ask the question, does it really have to be a black hole? And we have seen several effects of general relativity now in significant detail. The first one is when you have a star approaching a very heavy mass, and the star sends light to us, then as it is near the star, at the black hole, the light has to climb out of the gravitational potential and loses energy. This is called gravitational redshift, and can be seen as a redshifting of spectral lines relative to the Newton orbit, which is here a flat line as a function of time, to the red. So in Newton, you would only see a horizontal flat line, while general relativity would give you the red line, and you can clearly see that the measurements we were able to take clearly, confirm general relativity.
Pues no solamente comprobaron que eso sí es un agujero negro, sino podían aplicar pruebas finas de la relatividad general. Por ejemplo, si una estrella pasa muy cerca del agujero negro, la luz tiene que subir un gradiente de gravedad y se cambia de longitud de onda. Eso se puede medir comparándolo con una estrella en gravedad de Newton. Y eso en esta gráfica se ve perfectamente con gran precisión que ocurre.
Okay, the next effect general relativity predicts is that orbits of stars orbiting a big mass like a black hole don't close anymore. So in Newton's theory, if you have a single sun and a single planet, then the planet would go for all times in the same orbit. Not so in general relativity. In general relativity, the stellar motion precesses in the orbit of the star in prograde direction, as well as if the black hole has spin, it wobbles around the spin of the black hole.
Pues otro efecto es el cambio de la órbita de la estrella. En la gravedad de Newton tienes una estrella o un agujero negro y una estrella. La órbita se cierra y se mantiene cerrada, pero en la gravedad de Einstein la órbita cambia, se tuerce, se precesa y también no se cierra en sí.
The way to make that visible for you is very much the same way as in the left side. If you plot the X and Y residual positions of the star relative to the Newton orbit, then of course in Newton, which is this black thing, nothing happens. All right, the star always is on the Newton orbit. But in Einstein's theory, because of this precession, you would expect these beautiful little loops due to the looping of the orbits. That's the red curve. And the measurements are the blue measurements. And you clearly see they do follow what Einstein's theory tells us. And that has, first of all, of course, the result that we've tested Einstein's theory here again, but more importantly, perhaps, it shows that there cannot be any other mass of substantial nature in the addition of the central black hole. Or it can be a binary black hole or a black hole surrounded by intermediate mass black holes.
Pues no solamente la curva roja es la predicción de Einstein, el punto grande es la predicción de Newton. Y los puntos azules son los datos. Y los datos obviamente confirman Einstein, pero además comprueban que no puede haber otras masas, incluso otros agujeros negros. Solamente puede haber uno.
Okay, now let's be clear. This star is still, in effect, however, orbiting at 1,000 Schwarzschild radii. So if you really want to be sure, we have to go closer to the event horizon. And that is possible too, in two ways. And that's sort of the final part of this discussion here. One is there's hot gas from Sagittarius A star radiating in the infrared every day for a few hours. And it turns out to be, when that emission comes, these flares come, that there's a hot gas cloud which is moving around the Sagittarius A star position on scales of about 4 times the Schwarzschild radius, the event horizon radius. And we can measure this, as you see down there below. It's always in the same direction, and it moves there at a third the speed of light, just about what you would expect from a 4 million solar mass black hole, but now on scales of the event horizon.
Y para llegar más cerca del horizonte de eventos, están utilizando las nubes de gas que circulan muy cerca, solamente 4 radios de Schwarzschild, 4 veces el tamaño de este horizonte, y pueden comprobar que también obedecen las leyes que se esperan de un agujero negro.
Okay, so far we've been using stars and gas, but now we remember the beginning of the talk, we have another tool, light. Light sees gravity, remember what I said before. And so the next piece of evidence we have available is to use light to test out the mass in the center. So imagine you look at a black hole, which is this grayish, blackish thing there. Look at it from the left side, and then imagine there's a light source, that blue little dot, behind the black hole. Then, as I described earlier today, of course, light which is bumping into the event horizon won't make it through, that's clear. But even light outside of the event horizon, the red rays here, also won't make it to us because they're bent so strongly that they eventually fall into the horizon. It's only outside, about 2.5 times the event horizon size, when the green rays go, that we actually can see them. So that prediction, coupled with the precision measurement of the mass and the distance to the galactic center we have from the stars, we can use with general relativity to calculate how big that central dark region, which we call a shadow, should be, and that should be 50 microarcseconds. And that's what the radio astronomers have measured last year. In the center, a dark region surrounded by a ring of light radio emission with a diameter of 51 microarcseconds. So that's exactly what we would have expected.
Pues desde la masa que ellos han determinado utilizando las estrellas y las propiedades de la luz, se puede calcular las órbitas de la luz emitida detrás del agujero negro y entonces predecir la distribución de luz alrededor de la sombra, que es la parte central. Y eso se predijo en la base de las medidas de las estrellas y, como todos sabemos, se midió por los radioastrónomos hace, en 2017.
Okay, so after 40 years, we've come a long way. We've started out at distances of a few light years from the central radio source, Sagittarius A star. We're measuring the first gas motions, and they already showed us that there was a concentrated mass. And we worked our way inwards. So in this diagram here, where mass is on the horizontal scale in logarithmic units, and on the vertical scale, and the horizontal scale is the distance. We were measuring always the same mass, as you see, always a few million, 4 million solar masses. But over time, over 40 years, we were able to push this to about 1,000 times the event horizon size, and we are sure that there's very little other than this central one mass. So this excludes almost everything you can think of. There are a few exceptions. You could think of dark matter collecting down in this region, but with the measurement of the hot gas, which I showed you, and the event horizon shadow, we now know the same mass holds for the central region also as for the stars. So there's no way out. This is a black hole.
Entonces, la gráfica muestra progreso durante 40 años. La masa de 4 millones de masas solares desde el principio. Cada vez su radio más y más restringido, hasta 1000 veces el tamaño del horizonte de eventos. Pero al final ahora, con la foto de radioastronomía de la luz alrededor, ahora sabemos que no hay otra posibilidad, ni materia oscura ni nada, solamente un agujero negro central de esa masa puede explicar todas las vibraciones.
Okay, are we done? Is it a black hole? Probably. We have not measured one property yet, and that's the spin. That's what we're trying to do this year and the next years. We'll see how far we get. But in the meantime,
Vamos a empezar un turno de preguntas, como siempre, y la técnica es visual, aunque yo no veo muy bien, pero alguien me verá. El que quiera hablar, levanta el brazo y se le da un micrófono a preguntar. Ya.
Bueno, muchas gracias. Una pregunta. He querido entender que el agujero negro, a medida que van pasando los años, el radio se va haciendo cada vez más pequeño. ¿Eso cuándo se va a parar? ¿O no se va a parar nunca? ¿O llegará un momento donde el radio llegue a cero?
Okay, so he's saying he understands that as time has gone on, you've reduced the possible radius. Is there a limit to that?
Is there a limit? Well, certainly the event horizon is the limit, there's no doubt about that. I think I can imagine that if we and also the radio community push on their techniques still more, we can go down to a few times the event horizon size, 2 or 3 times the event horizon size, measure the detailed properties of the gas there, etc. So I would say there is a good hope for detailed physics. As I said, we want to measure the spin, and at the end, the great triumph is to prove what's called the no-hair theorem. And that is, black holes are as simple as you can imagine. They have a mass, and they have a spin. Also electric charge, let's leave that out. Nothing else, no mountains, no valleys, nothing. You can tell your sons and daughters about it, it's very simple.
Pues él dice que con la mejoría de las técnicas de radioastronomía es posible llegar un poco más cerca, quizás 3 veces el tamaño del horizonte de eventos, y tiene que medir una propiedad más, que es el giro, la rotación, spin se dice, cuantificarla. Y la predicción teórica es que los agujeros negros son muy simples, solamente tienen 2 propiedades realmente, la masa y el spin, nada más, no tienen ni átomos ni moléculas, solamente 2 propiedades, es muy simple. Pero eso está por verificar, es la predicción.
Hi, I will ask in English. You said at the end that the hypothesis of a black matter is discarded. So my question is, if you will discard the hypothesis of the black holes, which are the alternative hypotheses to explain your observations, such as, for instance, I don't know, a black matter vortex in a high-speed turning, or I don't know, or even hypotheses outside the relativity theory? I don't know, there should be alternatives. Thank you.
There should be alternatives? Really? Do you know about them? Well, look, I think it's clear that a scientific statement, if I'm here in front of an expert audience, I would say you've excluded that the central mass is largely due to a dark matter concentration. There could be dark matter, so to speak, tagged onto the central massive black hole. There could be stellar black holes at a modest amount surrounding this big black hole. But, I mean, as a first order statement, yeah, that looks like a black hole. If you have alternative ideas, go ahead, publish them, and we'll try to check.
Bueno, entonces él dice que, bueno, han establecido que es un agujero negro, no se ha excluido un poquito de materia oscura alrededor o algunas estrellas, objetos de masa estelar, agujeros negros, pero mucho más pequeños. Eso no se han excluido. Si alguien tiene una hipótesis muy diferente, obviamente hay que publicarlo. Y entonces los observadores experimentalistas lo van a comprobar, pero hasta ahora no hay tal hipótesis.
Buenas noches. Todas las galaxias tienen como núcleo un agujero negro, y luego preguntarte también si todos los agujeros negros son candidatas a tener una galaxia a su alrededor.
Okay, so all those have black holes, and I think he also said whether all black holes are at the center of galaxies.
Okay. I would say that the evidence as we have it is that the hypothesis that all massive galaxies, not very small galaxies, massive galaxies, have a central black hole since a few giga-years after the Big Bang, I think that's probably very likely. Have you checked every single galaxy? No, we have not, of course. But statistically, that's certainly significant. The thrust of current research is to try to find out, who was first. Was the black hole first, or was the galaxy first? Who grew fastest at the earliest time? And the James Webb Telescope, about which there will be a talk here in 2 days, is doing exactly that, trying to trace back the history of galaxies to, in fact, remarkably only a few 100 million years after the Big Bang, much earlier than we actually would have thought. And they see black holes there as well. So in that sense, the story does seem to look like black holes in the centers of galaxies, and galaxies grow together, roughly speaking. Now the details we will, of course, have to see. When you say a black hole is in the center, what does it mean? Is it nailed there to a point? No. It's just sitting there in a gravitational potential made up by the galaxy. It really does actually slosh around there a little bit at a slow speed, but it's not nailed to the central point.
Bueno, a ver, él dice que todas las galaxias masivas, grandes, sí parece que tienen agujeros negros masivos en sus centros. Obviamente, eso es un dicho estadístico. Es imposible medir todas las galaxias para ver que eso es verdad, pero hasta ahora sí. Por punto uno. Después, la pregunta, ¿quién llegó antes, el agujero negro o la galaxia? Hay evidencia ahora, reciente, del James Webb, de galaxias que se han formado muy cerca del Big Bang, relativamente cerca, y mucho más cerca de los teóricos pensaban, y que son masivas y que tienen agujeros negros. Entonces, la idea general es que ni una ni otra forma antes, se forman mutuamente. Mientras se forma la galaxia, también se forma el agujero negro. Y después añadió que la idea de tener este agujero negro masivo en el centro de la galaxia, como si está pegado, pues no. Tienen un poquito de movimiento lento alrededor del centro de masa, pero no mucho.
If I may ask in English, does the spin property in black holes behave similarly to how it does in subatomic elementary particles, or did they just share the name? Thank you.
I don't understand.
The spin property in black holes.
The big property.
The spin. Does it behave like it does in subatomic particles, or it doesn't?
Well, I mean, it's a macroscopic quantity. I mean, it's not tagged to a single subatomic unit. So it's many such units together. So it's a classical quantity.
Sí. La pregunta era si el spin de un agujero negro es clásico o cuántico, y la respuesta es que es clásico porque se trata de una unidad macroscópica, no microscópica. Sería clásico.
¿Por qué las galaxias giran en redondo, pero nunca son esféricas, es decir, como si fuera un planeta, me refiero, o una estrella, sino que son, entre comillas, planas?
Pedro, repítelo.
Que las galaxias no adquieren una forma esférica, sino más bien plana.
He asked why our galaxies not generally spheroidal, but let me answer that, because that's the subject of my talk. Con permiso de Reinhard, yo lo voy a contestar. Mi contestación es, ven el jueves. Eso sí es una parte de mi charla.
Well, if I may ask in English, we know that now, due to Hawking radiation, that we can get some information about black holes, but I'm not sure what kind of information can we obtain about a black hole, because we know that there's certain information that escapes from it, but what kind of it?
Okay, may I, shall we say, not correct you, but at least make a slight change of your question. You said we know from Hawking radiation. We don't know Hawking radiation. That's a hypothesis. It's a very plausible hypothesis for anyone who understands quantum theory. That's very likely, but it's not observed. We don't know anything about it. So I'm a hardcore experimentalist. You don't have to believe anything unless you have seen it. So therefore, we should look for Hawking radiation. Can we see it? And the answer is, I'm afraid not, because Hawking radiation is basically, its strength is governed by the curvature of space-time at the event horizon size. And so, for the big black holes I've been talking about here, that is equivalent to temperatures of 10 to the minus 25 degrees, so we can not ever hope to see this. So if you wanted to see Hawking radiation, your best bet is in a subatomic collision, making a very small black hole. But that is not possible with the current accelerator. So whilst I'm excited about the possible deviations in Hawking radiation from thermal radiation, which may have the information paradox answer in it, don't say we know from Hawking radiation.
Bueno, entonces la pregunta es ¿qué información podemos extraer de la radiación de Hawking? Y la respuesta es que no sabemos si realmente la radiación de Hawking existe porque nadie la ha podido detectar. Y es muy difícil de detectar. Depende de la curvatura del espacio-tiempo alrededor del agujero negro, y la mejor forma sería en los muy pequeños diminutos, pero entonces son temperaturas de 10 a la menos 25 grados. Realmente, básicamente, para decir una cosa, yo creo que es la razón por que el pobre Stephen no recibió el Premio Nobel, porque predijo algo magnífico, pero nadie se podía comprobar.
Hola, buenas tardes. Yo quería hacer un par de preguntas. Primero, si existe un límite, digamos, máximo y mínimo para el tamaño de un agujero negro, o tamaño masa, y que a partir de qué distancia, digamos, podríamos notar aquí en la Tierra los efectos gravitacionales del agujero negro, digamos, de un tamaño estándar. Gracias.
Well, okay, so empirically we know that for massive galaxies, again, massive galaxies, the fraction of the mass of the entire system in baryons, in normal matter, is about 0.3, 0.4% of the total. Okay, so it's a significant but modest amount. In lower mass galaxies, there's very little evidence for black holes at this point in time. That may be a question of measuring it, but we don't know. Is this a sort of a natural constant of nature? No, it does not. It has to do with, in fact, the processes which lead to the formation. The sizes are totally determined, of course, by the mass. So if you have a few million solar mass black hole, like at the galactic center, that is a few solar radii in sizes, while the biggest black holes are 1,000 times that. So they like the entire solar system. What was
and what would be the effect?
The Earth, the effect of Earth. Well, okay, I mean, we are now in what I would call the geriatric part of the universe. Why am I saying this? We are in an expanding universe, and perhaps the answer everyone would have expected naturally is that if you have an explosion and you have a finite mass, then of course the explosion at some point will work against gravity and come to a slower and slower point, zero, and then everything collapses again. That was the expectation, but that's not what the measurements show. The measurements show that the expansion of the universe accelerates exponentially. And that means that the amount of material which falls into galaxies is decreasing very rapidly. But the material falling into galaxies leads to star formation, and in second fashion, so to speak, to the feeding of black holes. So whilst black holes, massive black holes, quasars, in the early universe were extremely active and often on, actively radiating. Nowadays, that's very rarely the case. And this little small black hole in our galactic center, is a not very impressive guy actually on all of these scales. Nevertheless, if there would be some moderate amount of accretion, we would not see it here. In a quasar, that's a bit different story. If you would have been born 10 billion years ago in a big galaxy which turned quasar, then again, better get the insurance, because that would have been dangerous.
Bueno, ¿dónde empezar? Él dice que el tamaño de un agujero negro depende solamente de su masa, punto uno. Que la proporción de masa de un agujero negro a su galaxia es menos de la tercera parte de 1%. Es decir, puede ser un objeto individual muy masivo, pero frente a la masa de su galaxia es muy modesto. Punto 2. Con lo cual, los efectos gravitacionales son limitados, no son profundos. Ahora, si un agujero negro atrayendo masa puede llegar a ser un quasar con mucha actividad que puede afectar a la galaxia, eso sí ocurre. ¿Qué pasa? Que ahora estamos en una parte tardía del universo. La parte del universo donde había muchas galaxias, muchos agujeros negros grandes y mucha formación estelar y muchos quásares, está ya hace 6 billones de años. Con lo cual, la cantidad de masa que puede caer a nuestro agujerito negro central no es tanto. La probabilidad de que haya algo que afecte a la Tierra es muy pequeña. Si hubiéramos vivido en una galaxia hace 6 billones de años, entonces sí, hubiera sido necesario, como dijo él, sacar una póliza de seguros contra el quasar. Pero aquí no hace falta.
A ver, ahí arriba, que nunca damos la palabra a las alturas, había alguien que hace rato estaba levantando la mano. Dos. Como no tenéis micro, tenéis que gritar un poco para que yo, sobre todo, si lo decís en español, lo oiga, porque si no me va a preguntar a mí y yo estoy tan sordo como él, o sea que habla fuerte, por favor. Vamos a ver, John. Pregunta por los agujeros negros supermasivos, que si siguen un poco las mismas características de los normales o tienen algo de especial.
One of the biggest black holes have properties which are different from those
No. I mean, I think this is the question, of course, how big can galaxies get? And yes, it is certainly true that over the last 10 years, a few more massive, really massive, 10 to 10, but I don't think they need a different pathway for formation.
Bueno, la respuesta básica es que el tamaño enorme de un agujero negro depende de una galaxia enorme. Y es cierto que en los últimos 10 años hemos encontrado algunos de los más masivos que están distantes, pero las propiedades no difieren básicamente de los que están un poco más pequeños. Son muy similares o iguales.
En los gráficos habituales que se ven de los agujeros negros y demás vienen representados también con eyecciones de energía perpendiculares al plano galáctico. ¿Hay indicios observacionales de que en nuestra propia Vía Láctea existan este tipo de eyecciones, aunque sean mínimas o antiguas?
So he's asking basically about the jets, the activity perpendicular to the plane that occur in certain galaxies. Is there any indication of a similar phenomenon in our galaxy?
First off, let me say that assumption is not correct. Black hole activity is local politics. What I mean by that is that, a black hole in the center of a galaxy gets to see what the galaxy serves in terms of the meal. And it is true that the galaxy on a large scale, say, is in a plane like this. But locally, the gas can come from here, from there, from there, from there. In particular, in galaxies like our own, where there's relatively little material in the center. So the angular momentum, which we now know of the central region, we've measured this now, has nothing to do with the Milky Way plane. We also have not seen it yet, by the way, which may be a result of the fact that the black hole in the galactic center, specifically the galactic center, has low rotation, low spin. But that's just a plausibility argument.
Pues él dijo que el agujero negro central no comparte la dinámica global de la galaxia. Él dijo que es política local, como dijo él, y que entonces la dirección del vector momento angular no es necesariamente lo mismo que en la galaxia completa. Y no han detectado uno de esos chorros en nuestra galaxia de momento. De todos modos, no estaría perpendicular al plano. Es interesante que hay objetos perpendiculares al plano de la galaxia que vienen del centro, que se llaman las burbujas Fermi, pero no son exactamente lo mismo que el tema del agujero negro.
Hello. So I think you said before that the size of black holes depends only on their mass. So I was wondering if the density of all black holes is always the same. If the density of every black hole is the same.
Density in what sense? Inside the black hole?
Yeah.
No, okay, well let's not go there right now, because that opens a whole different discussion, because when you are inside the event horizon, okay, I didn't discuss this because of time. When you are inside the event horizon, say you are there with your rocket and your family trying to take a vacation there, you fly in, you won't be able to stop, ever. You'll just fly in finite time to the center, to the mathematical center. That is a point. And everything which comes in there ends up there. There's no, nice structures in between, hotels and that kind of stuff. It's just falling into a singularity. So, and that's why the question, what is the mean density inside the event horizon is not, so to speak, does not make sense mathematically.
Sí, la pregunta sobre si las densidades de todos los agujeros son similares o iguales, no es posible contestar eso porque no hay una densidad promedio dentro de un agujero negro. Si alguien entra, cae automáticamente al centro, al punto singular en el centro. Y no hay más que decir, no hay un promedio posible de la densidad. Perhaps, what about whether the ratio of event horizon to mass what is the function?
Well, that's a spin. I mean, it is certainly true that if you wanted to know what is the size to the mass ratio, then that's the spin. Yeah. If the object has a lot of spin, then it's much smaller because the event horizon is smaller. But there, I would say again, we know too little about the spin at this point about black holes.
Sí, si solamente se trata de la razón entre el tamaño del horizonte de sucesos y la masa, eso depende del giro, depende del spin, y no sabemos suficiente del spin todavía.
¿Qué teoría hay sobre la función que pueden cumplir los agujeros negros así en general? Porque, por ejemplo, podrían ser portales dimensionales dentro de la física cuántica.
A ver, ¿puede repetir?
Sí, repito. ¿Qué teoría hay sobre la función que pueden cumplir los agujeros negros, así en general, y si pueden ser, por ejemplo, portales dimensionales dentro de la física cuántica?
¿Qué función tienen los agujeros negros? Y si pueden ser portales de la mecánica cuántica para, no sé si para ir a otra dimensión o algo así.
¿Portales a qué?
A otras dimensiones.
I'm just a simple experimentalist. Sure, I mean, there are mathematical solutions called wormholes, where you take a black hole and another black hole from a different universe, and you stitch them together very carefully. We must be really careful. And so careful that, even Trump couldn't do it.
Sí, dice que hay solución matemática.
Okay,
hay soluciones matemáticas que si tienes dos agujeros negros y los acoplan con muchísimo cuidado, hasta el propio Trump no lo podía hacer. Pero claro, la política es local, ¿no? Y no global.
What do I know?
No, son fantasías.
¿Alguna pregunta más?
Arriba.
Ah, arriba. Los de arriba me tenéis loco, gritad.
Vale, porque yo tengo entendido que nada puede salir de los agujeros negros, y entonces la energía que libera no debería no poder liberarla.
A ver, repítela, por favor.
La energía que libera el agujero no debería no poder liberarla porque nada puede escapar.
Como nada puede escapar de los agujeros negros, la energía que liberan no podrían liberarla realmente tampoco, lo que dicen. ¿No? Que estoy interpretando un poco la pregunta.
From black holes, how can they liberate energy? I don't understand the question.
Well, they liberate energy when material falls in, okay, outside of the event horizon. Once the energy, in terms of mc squared, is inside of the black hole, it'll end up in the event horizon, in the central singularity, period. The mass grows, so to speak, or the energy grows, but it cannot escape, other than the potential of the, the Hawking radiation, but that is not a practical solution for a big black hole. It could be a little bit practical for a very, very, very small black hole, but not a big black hole.
Entonces, al caerse a un agujero negro, la masa se puede convertir en energía fuera del horizonte. Y esa energía sí se escapa como radiación que se ve. Pero una vez dentro, entonces inevitablemente todo va para el centro, para la singularidad. De eso no hay escape, salvo por la hipótesis de la radiación de Hawking, pero la radiación de Hawking en la práctica solamente tiene una pequeña posibilidad de los muy pequeños agujeros negros, no de los grandes.
Okay, well,
No sé cómo es la hora.
La última.
Hola, gracias por hacer la última pregunta. Mi duda es, si previo al Big Bang toda la masa estaba concentrada, ¿no sería como una especie de agujero negro y en ese caso cómo pudo salir la materia de ahí y explotar? No, esa es mi pregunta.
In the Big Bang, all the mass in the universe was concentrated. Were there black holes before the Big Bang?
Oh my. Where's the answer? Well, I'm not allowed to escape. I'm inside of the event horizon. Well, let's see. It is certainly, I would say, not possible, given what we know about physics, to make any statements about things before the Big Bang. Okay, let's leave it at that. There's speculations. In multidimensional universes, you can make speculations. We don't know whether we live in such a universe. What you can ask, and that is being asked right now, in fact, quite intensely, since dark matter plays such an important role in forming the structure of the universe on large scales, yet a possible dark matter particle has not yet been identified in a laboratory. Whether black holes formed in the very early phases after the Big Bang could have been the carrier of dark matter. That's being very much intensely discussed right now. There are parts of this proposal which can be rejected right away. If they're too big, then you can see them through gamma radiation and so forth, which is not seen. But if they're small enough, then they might escape detection. And can one see them? Actually, we might. We might use the same instruments which we are using for the Galactic Center to hunt in the Milky Way for mid-size black holes which cannot be produced as stellar black holes. So I would not at all be negative to say, this cannot never be checked. Maybe it can be checked now.
Bueno, punto uno. No se puede hablar de forma significativa de qué pasó antes de la gran explosión. Alguien puede especular, sí, pero hablar bien, correctamente, con física, no. Otra historia es si la materia oscura, que sabemos por su gravedad, tiene de una forma u otra que existir, podría consistir en agujeros negros. Y eso no está totalmente excluido. Eso no es, dado que la búsqueda de la materia oscura no ha sido infructuosa, la hipótesis de que podría consistir en agujeros negros que se formaron no mucho después de la gran explosión, es una hipótesis que se puede explorar, incluso con las técnicas relacionadas con las técnicas que están desarrollando ahora en su grupo y en otros grupos. Eso tiene sentido. Y aunque hay diferentes tamaños de agujeros negros que no pueden ser muy pequeños, pero es posible que de tamaño intermedio puedan formar la materia oscura.
Nos gustaría continuar, pero los trabajadores de esta casa tienen que cumplir un horario y ya lo hemos pasado. Os agradezco que estéis aquí y os recuerdo que mañana también va de agujeros negros. Viene el director del IAA, Anson Alberti, que va a hablar de cómo se fotografió por primera vez un agujero negro, que lo habréis visto hace unos meses en todos los medios de comunicación, y de eso veis la charla mañana. Y aprovecho también, aunque poco a poco iré dando píldoras estos días, para animaros a que paséis por Diputación a ver la excelente exposición que tenemos allí del Observatorio Astronómico Astroita, que están aquí hoy con nosotros también. Y nada, agradeceros que estéis aquí, que les deis un aplauso a nuestros invitados.